Welcome to the second part of the problem-solving session for Chapter 24. Let's begin where we left off, and that is question 7. Here, we are told that there's charge uniformly distributed over a very large flat sheet, and it's horizontal, and the charge per area sigma is given to us as positive 9 microcoulombs per meter squared. The question is to find the electric field just above the middle of the sheet. In other words, somewhere where it's not near the edges. Well, we know that this is a very large sheet, and so that provided we keep the distance where we're calculating the electric field relatively short compared to the dimensions of the sheet, then we're assured that we can get an accurate value. Now, we are given the choice. We could use a cube if you like, or we could use a cylinder if you like for our Gaussian surface. Of course, the cylinder would make a cross section here as it cuts through, and there would be charge inside, and then of course it would come out the back, so there would be a top and a bottom and curved edges that we have to take into account for the surface area of our Gaussian surface. All right, well, let's see. The electric field will be radially outward from both the top and the bottom, and so the electric field and the area normal of the top and bottom are parallel. On the other hand, in the curved section, although the electric field is up, the area normal is out, and therefore there will be no contribution from the area normal. So, two contributions from the top and the bottom of the Gaussian cylinder, and the charge, which is inside this right here, is given by sigma times the area of the cylinder, pi r squared. And this is the cross-sectional area that cuts through the sheet. So this becomes the charge inside of the Gaussian cylinder. Well, let's see. Sigma times pi r squared over epsilon naught, 2 times the electric field times the area of the cylinder, and of course 2 times means we're taking into account the top and the bottom, and that equals sigma times pi r squared over epsilon naught. But look here, pi r squared cancels on both sides, and therefore the electric field is calculated as sigma divided by 2 epsilon naught in the r hat direction, which means basically it doesn't have a spatial dimension. Well, let's go ahead and put in our numbers. 9e to the minus 6 coulomb per meter squared divided by 2 times 8.85 e to the minus 12. And this is in the r hat direction. We get a value of e, which, if my calculation is correct, is 5.08 e to the 5 newtons per coulomb along the r hat direction. Okay, last problem. Here we are given a combination of 2 types of charge distributions. One, which is a solid insulating sphere, which is concentric with a conducting shell, which has a radius, which has a width, because the inner radius is b and the outer radius is c, so it has a little bit of an interior. And the solid insulating sphere is itself has a radius A and has charge distributed over its volume. So we have two types of objects that we are going to have to be concerned with. Both of them carry a charge, except the solid sphere has the charge uniformly distributed over its volume, but the conducting shell has charge that can only exist along its surfaces. Why? Because it's a conductor. So any charge must exist along the surface, but we have an inner surface B and an outer surface C. Now the total charge, we're told, on the solid insulating sphere is plus 3Q. And remember that the charge will grow as we move out from the center of the sphere to the surface where it has the maximum amount of positive 3Q. On the other hand, the charge of the shell, both on the inside, and on the outside, oops, we lost our color here, on the outside, add up to, let's see, minus Q. Okay, some of it will be on the inside, some of it will be on the outside, and it's our task to figure out what is on the inside and what is on the outside. Well, what is going to happen here is that because there is positive 3Q, let me go ahead and use the red color here, sitting very close to the inner surface, and this is a conducting material, which means that the charges on the surface can experience charge polarization. Some of that charge will sit on the inner surface, and if you ask yourself how much, well, it's obvious that it would be minus 3Q because there is a positive 3Q sitting here. But the shell itself has a total of minus Q. So what must be sitting on the outside if the inside, the inner shell, has a charge of minus 3Q? Well, if we do the arithmetic, we know the total has to be minus Q, so there must be plus 2Q, which is on the outer surface of the concentric shell, of the conducting shell, that is. Okay, so once we have reasoned this, we can proceed to answer the questions that have been put before us. The first question, part A, says, find the charge, what is the Q inside a Gaussian surface that has a radius which is greater than C? Well, let's see. If we come over here and put a Gaussian surface with a radius greater than C, and we ask ourselves, what is the charge inside? Well, all we have to do is count. Plus 3Q minus 3Q plus 2Q. Well, that is equal to plus 2Q. Another way we could do this is to take plus 3Q minus Q, because that's the total of inner and outer, and that gives us plus 2Q. So the charge in the case where the Gaussian surface is greater than C is equal to plus 2Q, and that's the charge inside the Gaussian surface. The next thing we're asked to determine is the direction of the electric field out of the Gaussian surface. Well, because the net amount of charge inside is a positive charge, it must be that E is along the positive r hat direction. So E is radially outward. And of course we know dA will also be radially outward, and these two are parallel. So rightfully so, in part C, we're asked to determine the value of the electric field. Well, we know it's going to be, oops, before we go ahead, let's get a little eraser here and erase that. Let's go ahead and just work with Gauss's law. We know that the area of the Gaussian surface is 4 pi r squared. We know the charge inside is plus 2q divided by epsilon naught. E, therefore, now we're ready to write it as a vector, 4 pi epsilon naught is k. E, therefore, is equal to plus k times 2q divided by r squared. And so we're going to leave this in symbolic form because there's an r hat vector here, because they didn't actually give us any numbers to work with. So that's the electric field for r greater than c. Next, what is the charge inside? So this is D now. What is the charge inside a Gaussian surface whose radius is less than c but greater than b? Well, let's come up here and identify where this might be. Greater than, less than c. Let me make sure I wrote that. Less than c, yes, less than c, but greater than b. Well, it has to be someplace like this, right? In the interior, because that's less than c and greater than b, in the interior of the conducting shell. Now, of course, we know we cannot have any charge inside, since, after all, this is a conductor. But look what this tells us, that if we confine ourselves to what is inside or within this blue line, which is our Gaussian surface, there's the radius r, plus 3q minus 3q, which of course gives us a q inside, which is 0, right? Plus 3q minus 3q equals 0. And so therefore, if asked to determine the electric field, we know it must be 0. Good. Moving along. Now, in part E, we're asked, oh, actually, this was part E. And again, let's just write down Gauss's law, E times 4 pi r squared, but Qn equals 0. Therefore, E is equal to 0. Okay, F. In part F, we're said construct a Gaussian surface and find Q at r less than a. Well, at r less than a, we have to take into account the fact that, let's come up here, at less than a, we've got smaller quantities of charge than plus 3q. See, we are within the insulating sphere. And so we must take into account that the ratio of 3q, the total charge on the sphere, over 4/3 pi a cubed equals lesser quantities of charge over 4/3 pi r cubed. Well, again, we can see 4/3 pi cancels, and so the charge inside Qn is equal to 3q r cubed over a cubed. Well, now we're ready for the last part, which is to find the electric field at this location at r less than a. Well, E times 4 pi r squared, the area of our Gaussian surface, Gaussian sphere, Qn, 3q r cubed over a cubed epsilon naught. Notice that 2 of these r squared cancels 2 of these, And so we're left with the 4 pi epsilon naught is k. E is equal to 3qr over, let's have our k here, over a cubed. And this is r hat direction. Okay, how about one thing that we weren't asked, and that is, what if we wanted to know the charge which is contained in a Gaussian surface whose radius is greater than A but less than B? We weren't asked for that. Well, let's do that real quick. So this would be it. R here, let's make a part GH. What is Q for R? Greater than A, but less than B. Well, in this case here, if we come up, you can see that the only charge inside here is plus 3Q, since that is the total charge on the insulating sphere, and none of the conducting charge is there, is inside. So plus 3Q. And so here, if we want to get the electric field, GHI, or IHI, E times 4 pi r squared equals 3Q over epsilon naught, and this becomes E equals 4 pi epsilon naught is K, 3Q over r squared in the r hat direction. Well, this concludes the last part of the problem-solving session for Chapter 24. Until next time.